Alright, here we go. The class example for chapter 24's mean of differences. So we have indicator of physical fitness is our resting pulse rate. So they have 10 men that volunteered to a tested exercise device as seen on TV, and they're going to use it 3 times a week for 20 minutes. Resting pulse rates were measured, before their testing began, and then after 6 weeks of this physical fitness program, they measured resting pulse rates again. So the results of this are in the table. So you have these men and their before pulse rate and their after pulse rate. We'll enter those in our calculator in a minute, but that's the data. So it's kind of like list 1 is all the before values, and there is an average for all those values. List 2 is all the after values, and there's an average for all of those. We're not comparing the average of the befores and the average of the afters. We're going to compare the difference, the mean of all the differences. So we're going to look at Alan and calculate his difference, Brandon, calculate his difference, and so forth, and then use this new third column of differences and run our inference test on that. So the question we have is there evidence that this kind of exercise program can reduce resting pulse rates, and if so, by how much? So this is basically saying do a hypothesis test and then do a confidence interval. That tells me what my expectation would be for how much it reduces it. So chapter 23 is not going to work. We certainly do not have independent data here. I mean, we got Alan before and after. His before score and his after score, those are certainly not independent events, because they're all about Alan. What we do is we make a third column where we're going to get the differences between the before and after scores. So they're paired up, and we're going to use one sample T procedures. So our hypothesis, the null hypothesis, is that the mean of the differences is equal to 0. And that is a notation you want to use. The mean of the differences there. On average, in words, on average, the exercise device does not reduce resting pulse rates. Remember, the null hypothesis needs to represent the idea that nothing special has happened. The alternate hypothesis is that the mean of the differences is less than 0. In other words, on average, the exercise device reduces the resting pulse rates. So again, here, pay attention to the direction. The sign here, we're looking for the mean of the differences to be less than 0, meaning that the pulse rates went down. Okay, so when we're creating our new list 3, we want to make sure that we're creating it in a way that matches this alternate hypothesis. So the results of the exercise program are independent between Alan and Brandon and the rest of the guys, but the measurements themselves are paired by subject, and so they are not independent from one another. But we do have a paired set of data. The men volunteered, so it's not a random sample. However, it seems reasonable that we could say that these guys are representative of the population. If you want to question that, you could, but remember, the idea here is that we don't want to stop at this point and say that we can't go on. We want to go on. So you could say something, I'll proceed with caution. Anyway, just to make sure that we haven't, since we don't have independence, we want to make sure that we don't have too big of a sample. We'd have to assume that there are, these 10 men is less than 10% of all the men that would use the exercise device. And since it's as seen on TV device, we're sure that millions of people are using it. Alright, if we make a histogram of the paired differences, we would have that. You know what? At this time, I'm going to back up, and I'm going to enter this data in my calculator. The before in list 1, the after in list 2. So here I've put the before and after data in the calculator. Now, since this is paired data, it is important that each row matches up, so you have the same guy here before and after in each row, and then you have to have the same number of data elements in each list for this to work. So what we're going to do, this is what before and then after, so I'm going to create a list 3. And in list 3, remember, go up to the title. I'm going to put in list 2 minus list 1, second list 2 minus second list 1, and that'll populate with all my differences for each row. And then list 3 is what I'm going to use for my inference. I'm going to do like a one sample t-test with list 3. So if you see my values are negative, that indicates, because of the direction we went, that indicates a reduction in resting heart rate. So by improving your physical fitness, you will these guys have shown that they have reduced their resting heart rate, which is the direction you want to go. So let's take a look at that histogram now. The histogram, you'll notice if you look at the X scale, it's got -1 up to, +7. So their signs for this histogram are actually the opposite value of mine. The shape of this is still going to be the same. We're looking for a unimodal and symmetric histogram. We just have a difference in the values. Actually, if you look at, I'll go back to my calculator. If I do my stat plot here and do a histogram with the list 3 here, I'm going to do a zoom stat, and I basically have a unimodal and symmetric graph here, the same thing here, but my values, you can see, are mostly on the negative side with just this other piece on the positive side. It's just the mirror image of this graph. It tells the same exact story. Okay, we move on. We're going to do a matched pairs t-test. Basically the same as a one sample t-test, except we're going to use a little bit different notation. Our sample size is 10, degrees of freedom n-1 or 9, and I'm going to need the mean of the differences. This we can use one variable stats on our calculator to get. Stat, calc, one variable stats, and I'm going to put in list 3. No frequency. And we get a mean of -2.8, the standard deviation 2.529. We'll use both of those. That's those, and we're going to need a t-score. Take a look at the t-score. It looks a little bit different. Our value we're working with here from our sample is the average of the d values, the average or the mean of the differences. Okay, remember we're just using the column that was just the differences. We get the mean of the differences minus the hypothesized mean divided by the standard error, which is the sample standard deviation just from list 3 divided by the square root of the sample size. So our t-score is -3.5. If we want a p-value from that, we can use our table. So here's our table. We have degrees of freedom of 9. We're looking for, well, it's -3.5. We're just looking for tail information here, so we'll just use 3.5. 3.5 is in between these two values we can see, so our p-value is in between 0.0025 and 0.005. Somewhere in between there. So we can see that this p-value, 0.0033, is in that range of p-values we got from the table. If you want to be more precise with this, the calculator can certainly be the route to take. To get a more precise value, we would need to use TCDF, so second distribution TCDF, number 6. The lower boundary, I'll just keep that in there for a super low number. The upper boundary, -3.5. Degrees of freedom was 9. And we plug that in, and there's the value that we had. 0.00336 and some change. Okay, remember you always want to make a graph, a sketch. And so here we are. We got our t-score there. We have our difference value marked on here. Those both go with this vertical value. And then there's our p-value, 0.0034. The only other thing we should do here is actually this needs to be shaded in. You should always shade in the area of interest. Kind of messy, but you get the point. All right, the conclusion, with a p-value this low, 0.00336, which you should probably write in here, we reject the null hypothesis. There's strong evidence that this form of exercise can reduce resting pulse rates, and it's not equal to 0. If this, we can go on to write this in another way. If this exercise program did not reduce heart rate, beats per minute, then the probability of seeing this reduction that we saw of 2.8 beats per minute or more, simply by chance alone, would occur less than 1% of the time, or only 34 out of 10,000 samples, just due to sampling error alone. So it reduces beats per minute. So then the next question is, by how much would we expect it to reduce the beats per minute? In our sample of 10 guys, it was 2.8 beats per minute. But what would we expect that to be? Certainly not exactly 2.8. So this is screaming for a confidence interval. It looks just like what we did in chapter 23, only notation changes here. No level of significance was given, so we'll just go with 95%. That's the most common thing that people use, especially if nothing is, no direction is given. So anyway, the 95% confidence interval, now look at this. So instead of X bar or Y bar here, we have D bar, which is the mean of the differences for our sample, plus or minus our T critical value at 9 degrees of freedom, times the standard error of D bar. This we already got on our calculator. Negative 2.8 is our observed values, and the T critical value for 9 degrees of freedom is 2.262. That needs to come from your calculator, so we're going to use inverse T for that, second distribution. Inverse T, we want the area to the left. It's a 95% confidence interval, so 0.025, only half of that 5% tail we're interested in. Degrees of freedom is 9. We'll paste that. And there's your negative 2.262. And if you crank all that out, you get negative 4.6 to negative 0.99. So we should, this verifies, first of all, that we've made the correct choice to reject the null hypothesis because 0 is not included in that interval. So what could we say? I'm 95% confident that 6 weeks of this exercise program can produce a mean decrease in resting pulse rate between approximately 1 and 4.6 beats per minute. Notice the language here and the context that also indicates the direction of the change. That's pretty important. Now that we've done all that by hand, that's actually the end of the example. But remember that all of this actually is doable on your calculator as well. So we already have our list 3 differences in the calculator. Let's see if we can verify this p-value and that confidence interval with the calculator. So I'll jump back here. I'm going to go to stat test. And what we want is a t-test because it's just a one sample. So just a t-test. I'm going to input, we have the data in there, so I'm going to use that. No, I'm going to use, the data, the hypothesized mean of the differences is 0. The list I'm going to use is list 3. And I want my mean of the differences to be less than 0. Let me calculate that. So there's my t-score, negative 3.5. There's my p-value. There's the mean and standard deviation. So all those other steps that we did along the way, one variable stats and all that, it could easily be replicated right here. So depending on what kind of work you need to show, it's always important to show the formula, plug in the formulas, and then you can crank out the values. This calculator can help you crank out the values quite nicely. Use your time wisely. The other thing we did is a confidence interval. So real quick, we'll go to stat test. We will do a t interval, number 8. And we already have the data in there. It remembers what we used last. We're going to do a 95% confidence interval and crank this out. And there are the same values. So make sure you're savvy with your calculator. Make sure you know how to use your tables. and on the resources you have.